Hello everyone. Today we are going to learn about isotopes and average atomic mass. A quick review about atomic mass. The mass of an atom is traditionally expressed in atomic mass units, abbreviated AMUs. This is because the mass of atoms is roughly in the area of 10 to the negative 27 kilograms, which can be a difficult number to manage. One atomic mass unit has a mass of approximately 1 proton or 1 neutron. It's not exact, but it's a pretty close estimate, and so for what we will be doing, we will be using this estimate. A reminder, electrons are very small. They have a mass that's about 1/1000th the size of a proton or a neutron. So therefore, for mass calculations, the number of electrons is traditionally ignored. So what is an isotope? An isotope is an atom of an element that has a different mass number. Some isotopes will be stable and will stay together. Others are not stable and will undergo radioactive decay naturally. So, what is different between each different isotope? Since the number of protons is unique to an element, all isotopes of a known element share the same number of protons. This means that the only other particle that has significant mass, the neutrons, will be the one that varies between different isotopes. For example, carbon-12 and carbon-14 are two isotopes of carbon. Both of them will have 6 protons. However, carbon-12 has 6 neutrons and carbon-14 has 8 neutrons. So, what is the average atomic mass? The atomic mass that is listed on the periodic table is actually an average atomic mass. You'll notice most of them are not whole numbers as we traditionally see for mass numbers. For example, the average atomic mass of carbon is 12.01 AMUs. This average is not found using the traditional method you would think of when you hear the word average. This is actually a weighted average, much in the same way that your semester grades are calculated using your quarter grades and your exam grade. The weights or percents that are used in order to determine average atomic mass are the percent abundances for the isotope. Basically, it is how frequently is that isotope found in nature for that element. The percent abundance is experimentally determined via a technique called mass spectroscopy. An example of the graph that is produced, a mass spectrum, is shown here on the right, where the mass to charge ratio is on the x-axis and the percent abundance is on the y. In order to make sure that you have done this correctly, you need to use a decent size sample to make sure that you have a representative sample. Think of it as you need to poll enough people in order to get a good answer for your statistics. The formula for determining average atomic mass is a weighted average formula, and so if you are familiar with weighted averages, this formula should look somewhat familiar. The formula is that the average mass is equal to the percent from isotope 1 times the mass of isotope 1, plus the percent of isotope 2 times the mass of isotope 2, etc., etc., until you run out of known isotopes. Note, in order to use this formula, the percents must be converted back into their decimal form. Otherwise, you will have to divide the answer to this by 100 at the end. So, for example, if one of the percent abundances was 55%, when you use it in the formula, it should be in its decimal form of 0.55. Let's look at an example. Using the mass spectrum that we have here, determine the average atomic mass for magnesium. So, first we have to determine how many isotopes are there. I see 3 isotopes, and we have to determine the percent abundances for each, estimated based on what we see on the graph. For isotope with a mass of 24, it looks like it is very close to 80 but just under, so let's estimate that at 79%. For the one with the mass of 25, it looks like it's exactly at 10%, so let's say 10%. And for the one who has a mass of 16, it looks like it's just above 10%, so let's call that 11%. And thankfully, because of how we estimated this, we did manage to add up to 100%, which is good. You will find sometimes that if you estimate this way, you might be slightly off, and that is okay. So let's plug them into the formula. Average mass equals 0.79 times 24, that's 79% in its decimal form, times the 24 for that mass, plus 0.10 times 25, plus 0.11 times 26, Following the order of operations, our multiplications must be done first, and then we add up the answers that we get, and we get that the average mass of magnesium is 24.32, which is very close to the mass that is found on the periodic table. Let's look at a second example going the opposite direction, trying to find percent abundances. Bromine has two naturally occurring isotopes, bromine 79 and bromine 81. The average atomic mass of bromine listed on the periodic table is 79.90 AMUs. Determine the percent abundance of the two isotopes of bromine. We will have to use a little bit of additional algebra on our average mass formula in order to find the answer to this. So let's plug in what we already know. We know that the average mass, 79.90, will be equal to 79 times whatever the percent abundance is for bromine 79, let's call it X, and plus 81 times, let's call it Y for the percent abundance for bromine 81. We don't currently know what either X or Y is. However, based on how percents work, what do we know about the percents X and Y? We know that the percents X and Y must add up to 100%. And so, in addition to 79.90 equals 79x plus 81y, another statement that we also know is true is that x plus y must equal 1, which is the decimal form of 100%. You can then rearrange this to substitute in. I have chosen here to rearrange x plus y equals 1 to substitute for y. Y is equal to 1 minus x. So 79.90 equals 79x plus 81 times the expression 1 minus x. Now we only have one variable present in the equation, so we can use algebra to solve it. Our next step is going to have to be distribution of the 81 across our expression. So 79.90 equals 79x plus 81 minus 81x. We begin to simplify, and we solve for x. X is equal to 0.55 or 55%. This corresponds to the bromine 79 isotope, so it will have a 55% abundance. However, we still need to find the percent abundance for bromine 81. Thankfully, this one will be much faster. We know that the percent abundances must add up to 100%. So let's use x plus y equals 1. We now know x, so 0.55 plus y equals 1. Solving for y, we find that the percent abundance for bromine 81 is 0.45 or 45%. And so our final answer is the percent abundances of bromine 79 and 81 are 55% and 45% respectively. Take a moment now and pause. Does this answer make sense? Does it make sense that they are very close to 50-50, but that there is slightly more of bromine 79? Well, if we look at the average mass listed on the periodic table is 79.90, which is very close to 80, halfway between 79 and 81. So it makes sense that they would be pretty close to 50-50. However, it is slightly less than 80, which implies that the smaller number, the 79, there is slightly more of. So yes, these numbers do make sense.